Hey, what is going on? It is January 30th, 2022, the big 3-0, and I have to say that, yeah, I was supposed to get into, start talking about the blood, the rest of the blood system, the plasma, and the life cycle of blood cells, and I do intend to get back to that. But honestly, I am really, really digging the brain chemistry and neuron physiology and neurophysiology stuff. I think it's really important to know, and obviously very important to the study of life and eternal life. We've got to keep our brain cells going. I think I remember watching this anime called Psycho-Pass, where one of the main villains, or one of the villains of the week, the monsters of the week villains, I believe, was saying that their brain has the ability to actually live 150 years compared to the rest of the body, which is really interesting on its own. And I don't know what studies they obtained to base that statement on, but I think I'm going to look into that for sure. And why would that be the case? Are the markers of senescence in brain cells, or the cause of senescence in brain cells, different? What is the difference there? So anyway, let's talk about. Let's go back to what our original topic. We can speculate on future physiology all day, but for now, let's talk about what we know. And yesterday I was talking about. I believe I left off at the brain, the neuron geometry and the neuron structures. And we talked about I have them displayed here. The main structures of the cell body, which is the soma, the dendrites, which give the quality of the neuron as to what kind of neuron it is, multipolar, unipolar, nonpolar, bipolar, etc. The axon, which is, I think, what people know about the most, and that is the long part that is responsible for transmitting the action potential signal, which is the information that the brain, essentially the information that is needed to make decisions, to allow the neurons to continue to function and create some sort of decision based on excitation of the action potential. Mine neurons right now are firing a ton because their action potentials are beating the threshold for some reason. And then at the end of the axon, you have the axon terminals, which contain the synapses, which is the other part people know about, and I'll talk about at some other point. But these are things I learned about that in high school, and the synapses are basically where the neurotransmitters live, which is really the hot buzzword for a lot of medium authors, persistently, who think about how their brain functions. Anyway, let's go back to the axon. Okay, so we talked about how the axon works, right? I don't know how deep I got into it, but essentially what happens is at this part, in the beginning of the axon, let's say this spiky thing is the dendricided neuron soma. At the junction between the soma and the axon, you have the axon hillock, which we haven't gone a ton into the function of, but that is really important because how that works is really how the rest of the conduction of the axon can function and produce the current needed to activate other downstream axons, or other downstream soma and thus axons, etc., etc. So at the axon hillock, you have this graded potential, which eventually there's a threshold that's surpassed in order for a current to be generated, and this would be the active area at peak of action potential. So basically what happens is once the action potential comes in, once the signal that surpasses the threshold comes in to the axon hillock, it will start a cascade of propagation of positive charge down. This region of positive charge will propagate down the neuron. Okay, so this region, I'll talk about how the geometry of this region is determined, but this region again moves along the axon, and this is called the depolarization region. So why is that the case? Because essentially, in a very quick nutshell, how that works is that Once there is a potential that is present here, the potential opens up, electric potential opens up channels, sodium channels. Sodium channels, they're not pictured here, but they will be in the next, one of the next pictures. The sodium channels are voltage-gated intermembrane or transmembrane protein complexes, which when and we'll go into the details. They're really interesting to me to learn more about how sodium channels work exactly on the protein and molecular level. But basically, once a potential is present on the sodium channels, they will get activated and allow sodium to flow into the cell. So why does sodium flow into the cell? Because normally the internal cell membrane is negative, okay? And the sodium will flow from a place, providing it's not blocked by a barrier, which in this case is the phospholipid bilayer of the axon, right? Because the axon is a cell, this is the cell membrane, which is blocked by the cell membrane. Now have an open conduction path into the cell, and thus the sodium will balance out the charge and create a negative charge outside, because a positive charge leaving an area will create a more negative charge. So the potential, the signs of the membrane, inside and outside, flip, where the inside is now temporarily more positively charged. And this temporarily more positively charged region, there will be propagation of this region through the axon, and it will stay that way as long as these sodium channels are open. What happens after some time, the sodium channels close again, and potassium flows out, right? And potassium flowing out rebalances the positive charge on the outside. The potassium channels open up when the sodium gets to a certain region here. The potassium channels are also charge driven, so they will open up and let potassium outside. And what will happen is the charge will polarize or repolarize. So the charge will become positive again on the outside, and as you can imagine, an animation of this, and you can find these online, indicate that this will be just how the stage after stage or section after section of the axon will, due to this flipping of charges inside and outside, positive charge inside to outside, will essentially move. This entire negative, the external region moves, flattens, moves through the axon all the way to the axon terminal here. So now let's look at what the graph of this looks like. So basically you have a threshold that stimulates the axon hillock, which then causes depolarization of a region of the axon, right? So once the region of the axon, that depolarization will occur until the action potential of that region is at its maximum, which is around 40 millivolts, I believe, and this graph shows it. And what will happen is, once the action potential is at its highest, then inside the cell, then the potassium channels will open up again and repolarize. So the sodium won't leave the cell right away. It'll be the potassium that leaves the cell. So what happens is the potassium leaves the cell and redistributes the charge. So what happens is a lot of potassium leaves the cell. Once the potassium leaves in a sufficient quantity, then this refractory period, which is dictated by the time it takes for the sodium channels to reopen. Because what happens is, you can think of the flowing in of positive charge along the terminal axon, along the axon, is due to only when the sodium channels are open. And due to pure physics, actually, the sodium channels need some time to reopen, okay? Because they close, then they reopen, right? So there's a physical requirement for the gating to reinitiate, and at that time, potassium needs to be put back into the cell. So potassium is put back into the cell during this refractory period to rebalance the positive charge to the resting state, okay? So we need to rebalance the positive and rebalance the the potassium concentration, right? Because a lot of potassium has left the cell, and essentially you need to overcorrect or rectify that voltage by sending more potassium back into the cell. And therefore the potassium and sodium concentrations, again, rebalance out to what they were before. I don't have the molarities of those, but I think they're pretty well known. They're like 150 molar of sodium outside, 30 molar potassium outside, 150 molar potassium inside, 30 molar sodium inside, and yeah, that's basically what happens. So now that was a quick kind of gloss over of how the potential propagates, right? And what is the curve of potential propagation for neurons. So actually, cardiomyocyte cells have a different action potential and a different action potential curve, which we don't get into now. But just to know that electrical activation is something that happens in both of those cells, neurocytes and cardiomyocytes. So let's talk a little bit about the nodes of Ranvier. I realize this is actually, we might get into this tomorrow. I just want to briefly go over it. The other thing people know about, and when it comes to Einstein, they know quite a bit about this, is that the axon isn't living in isolation. It isn't just a long piece of cytoplasm, the spaghetti noodle of cytoplasm, which connects to the axon terminals at another neurocyte. What it is, it is wrapped by myelin sheaths, right? So these are Schwann cells. And these Schwann cells actually extend from oligodendrocytes, right? So basically you have oligodendrocytes, which then create extensions around neurons. These extensions create extensions to neuron axons. The neuron axons are then wrapped by this fatty material called myelin. And this is kind of, a more realistic version of how it looks, right? Well, you have this one, and then you have this, right? So the myelin, it takes the form of Schwann cells which wrap the axon. And this wrapping of the axon allows a more efficient conduction of the action potential down the axon. Because without this wrapping here, would happen, the axons are often long enough that, due to basic physics in play here, as electric current travels down a line, resistance takes over and dissipates the current. So in order to prevent dissipation of the current due to resistance, which comes from various things, right? Resistance can come from the length that the current needs to travel down. Think about like a hot rod. You heat a rod at one end, and eventually at the other end, it won't be as hot. It'll be cooler, and the coolness will decrease with a steady rate down the length of that rod. It's the same thing. Due to frictional heating, that's why the heat doesn't propagate in the rod, and it gets lost in the environment. The same way the electric potential of the surface of the axon will get lost over a length of the axon. And so two ways that the body combats this, right, loss is the more conventional way is to create larger area neurons, but not larger area axons, because remember, the resistivity of an axon or of any wire is the resistance of any wire is due to the resistivity times the length of the wire divided by the cross-sectional area. So you can make really thick axons here, and that would reduce the resistance, but there's only so much of that you can do, right? The reason these evolutionary things happen, like Schwann cells or myelin sheaths or oligodendrocyte protection of the axons is due to many different iterations, and the body sometimes inability to accommodate a certain physical parameters, such as if your axons were all super thick, then your current wouldn't be lost, but then there'd be less room for your brain cells. It's as simple as that sometimes, and essentially that I don't want to ever say brain stuff is simple, but that's a pretty simple way of looking at it. And so then secondly, so the neuron itself diameter doesn't get thicker, the length also has to in some cases neurons have longer lengths, some don't, but essentially what this Schwann cell does is that this Schwann cell protects the current from leaking out, right? And that's one mechanism. The second mechanism is between Schwann cells who have a huge concentration of sodium channels, a much larger concentration of sodium channels. So these sodium channels allow reinforcement of the current. So even though current is lost, the Schwann cells do have a limited ability to allow. They don't have the infinite ability to allow the current to travel infinitely far. They have to, even though the current will travel farther along an axon, they still need to be reinforced occasionally with some more positive charge. So at these you can think of these as gas stations, these nodes of Ranvier, and they're sodium ion gas stations for your action potential. If your action potential is traveling, then it can refuel at these gas stations. So one might also question, why do you need the myelin sheets why don't you just refuel the whole way? Well, that's one way of doing it, but also that's super inefficient because you'd need a lot more sodium to refuel the entire length of the axon from the start to the finish. So why not just, instead of refueling, prevent the fuel from leaking? Think about the analogy. I've heard a good analogy as if the action potential were a car, right? And you aren't trying to travel down a highway. If the car was constantly losing gas, you could constantly take gas from the outside, right? But why don't you just make a more efficient car, like a new car, which then only needs to refuel? It still needs to refuel, but only at certain times, right? It can continue down the axon. It can continue down the highway. Got my analogies mixed up, without refueling all the time. So that's basically the structure of what these Schwann cells do via these myelin sheaths. Myelin is a fatty tissue, and it surrounds the axon, and and that's how signals are allowed to propagate. Now, neurons have different sizes of axon terminals, different lengths of axon terminals, different parameters for the size of the sheets, different parameters for the number of sodium channels at the nodes of Ranvier. But essentially this is what is happening here. Okay, so I think that's all that I want to talk about today. We could go into multiple sclerosis. I don't want to do that. That's a whole different topic. It does involve the same. It does involve the myelin and the destruction of myelin by immune cells which have crossed the blood-brain barrier. But for now, this is quite a bit, and I hope you enjoyed this video, and I'll see you another time.